Let's go on with the next presentation entitled Synthesis of Nonlinear Characteristics for the Mobile Robot Control System. Vasiliy Berdnikov, please.
Do you see it?
Yes, I can see it.
Okay. Hello to everyone. My name is Berdnikov Vasiliy, and first of all, I want to thank the organizers for this opportunity. Today, I will present the results of our work with Professor Valeriy Lokhin, and the title of work is Synthesis of Nonlinear Characteristics for the Mobile Robot Control System. But before I start, I want to say something about my previous work in the Department of Control Problems, and also about motivation to work on this one. So, in our department, automatic control systems are studied intensely in several ways. One direction of these studies is the use of fuzzy and narrow controllers in the low-level automatic control system. For many researchers, it is clear that intelligent controllers can deal with complex control objects in much better way compressed to the classical control algorithms. This happens because of their flexibility. However, proving stability and finding parameters in such controllers are still difficult tasks, especially when we talk about parametric disturbance objects, where we can only determine the range of change, but not the exact flow. In this regard, absolute stability theory can be very useful. On the one hand, we can deal with parametric disturbance, and on the other hand, we can find the stability sectors in which we must place our nonlinear characteristics of the intelligent controller. On the basis of Molchanov and Patinsky theoretical research, we are working on algorithms for Lyapunov function construction. And here I presented some results of how this algorithm works. This is level sets of this function. By Lyapunov function, we can only determine the stability or instability of the system, but we are interested in something more. Besides stability, we want to get some nonlinear characteristics for the controller, and also the worst possible disturbance in the feedback form. It helps us to determine the worst case scenario and get some guaranteed estimation of performance index. So we start to think in the way of differential gain. It is well known that most challenging task is to solve this partial differential equation, because the solution is continuous but not the smooth. And if somehow we find the solution, we can calculate optimal control and the worst disturbance in the feedback form by the following formula. It must be noted that these controls require full information about state vector x. And below we will call this type of controllers full information controllers or simply FIC. Moreover, if some additional conditions are satisfied, then the value function of the gain is also a Lyapunov function, and the control vectors brings asymptotic stability. That's why we decided to provide our own algorithm of value function approximation. I don't want to go deep inside formulas and backgrounds. I will just note some main features. It is mesh-free method with specially designed basis function, and it has efficient memory usage and fast gradient evaluation time for lower the system, which is very important in real-time application. So now we can move on. In our work, we consider one problem of trajectory tracking, where reference vehicle implement the ideal movement along some desired trajectory, and the mobile robot tries to minimize the deviation from this movement. On this first stage, we take a very simple model to provide general ideas, and here's the definition of error vector. After simple calculation, we can show that there exists stabilizing control laws U in assuming that linear and rotation speed are not equal to 0. Here is the structure of automatic control system. These blocks compute error vectors, and this is a full information controller, which consists of two parts, the controller itself and the conversion block. And one common way is to choose the control law in the next form. And it was proven in many papers that if coefficients k are defined as shown and parameters are positive, then system is asymptotically stable. However, we still need to choose these parameters precisely to provide good performance. And as we will see, this approach is not flexible enough to get the desired quality. Instead, we introduce our method. The main idea that rather than finding the concrete parameters and coefficients, we will determine the boundaries in which coefficients can change. So at this moment, we will think about k as function of error vector E. And to find concrete nonlinear characteristics, we will use the Valeriy function approximation. Let's look at the results. Here the trajectories of mobile robots with different controllers are presented. Ref is a vehicle moving in a circle counterclockwise, and it is clearly seen that FIC controller gives a better performance in comparison with constant parameter controller. It hasn't such oscillation and only a little overshooting right here. And CPC has large overshooting and oscillation long around trajectory. The same situation can also be seen on transit process. FIC controller about 2 times faster and has no oscillation. In the lower left corner, we give some data about tested controllers. For CPC, it seems like it's compromised between speed and quality, and a little bit lower. We show the data of the FIC controller, the boundaries of coefficients. And the last step of synthesizing nonlinear coefficients is to choose the integral criteria. We use common quadratic form, and again on the right, the advantages of FIC are clearly seen. It must be noted that synthesized characteristics are optimal, so we can't find a better one to improve choosing integral criteria. But we still have a question: can we have a better performance in terms of overshooting, speed, and oscillation? And the answer is yes. We can change integral criteria. Next slide provides comparison of 4 different integrals. The first one is unchanged, and the next 3 have significantly bigger influence of the corresponding components. So, for example, the L2 has domination of second component, and L3 have domination of third component. We can see that from all figures, L2 has the best performance with no oscillation and overshooting at all. Next slide proves this. We can clearly see the performance of left lower transit process. Here we present the nonlinear characteristics of FIC controller, and since it depends on all 3 components, we use the slides to show it. At the end, I want to present you general scheme of our method. So first of all, we determine math model of control object. The next step is to choose control system structure. Then we need to find the lower and upper boundaries of control system coefficients. After that, it is necessary to choose integral criterion. And with all this information, we approximate value function. Finally, if the resulting control is good enough, we stop, and if it is not, we try to change integral criteria and repeat further steps. Of course, like any other method, this one also has its advantages and disadvantages. Our method is easy to implement and can improve already existing control system. It's also computationally efficient for lower system. On the other hand, this kind of method is not cursor dimensionality free, and there is no, of course, open source software available. Future works will be focused on more complex mobile robots mathematical model and its physical realization, and also implementation of parallelization and maybe some sparse grid methods can help to avoid drawbacks of cursor dimensionality. So that brings us to the end of the presentation. Thank you for your attention and with some useful links.
Thank you, Vasiliy. Have anyone have questions? So, thank you again.